You know, I've got to adjust my slides so that they don't appear on this part that gets cut off up there, but that's the one problem with sharing the screen on here. By the way, I should also mention, just as a bit of housekeeping, that the recorded video from yesterday, and I intend to do this every day, underneath, if you look at the website, underneath today's date, yesterday's date, you'll see at the bottom of the list of things, which included the reading sections and all that, that the video is now posted. And I'm going to try. There are several stages of video processing that are required. Zoom does its own video processing, and when you do over an hour of time in class, that usually takes a while for Zoom to process it before I can access it, and then I upload it to YouTube, which has its own processing time required. And then I usually try to cut out the fluff at the beginning because I start the Zoom meeting, 5 or 10 minutes sometimes before class starts, and there's just a lot of dead time there. I'm going to try to go through the two first levels of processing and then post it by the end of the day. So if anybody does have to miss the class, in other words, they can't come physically to class and they can't come to the synchronous meeting, or if you just want to look at it again to get some detail that you might have missed, hopefully my plan is to do that every day so it's up on the website by the afternoon. This slide is a figure from one of Newton's publications. I can't remember which one it's from now off the top of my head, but it's one of my favorite figures because it was talking about the difference between physics and philosophy, and this was just along the same lines as what one of the major goals of physics is. This is a fictional kind of imagining of Newton saying, imagine there's a ridiculously tall mountain. Mount Everest doesn't stick up from the earth nearly this much. I mean, this is sort of a ridiculous, fanciful visualization. And you took a rock or something like that and threw it at a modestly large velocity, or projected it with some sort of cannon. Of course, it would fall to Earth at position D here. And if I projected it horizontally from the top of that mountain at larger and larger speeds, at some point, it's going to go into orbit, according to Newton, around Earth. And so in this one diagram, Newton is connecting up what before that point were really two distinct points of view in physics, which is how the heavenly bodies behave, how things orbit around Earth, and how at the point this was being discussed, we were thinking of things going around the sun. So how one body orbits around another, and the phenomenon of bodies just falling towards the Earth. When you drop a rock, that doesn't seem to have anything to do with the motion of a planet as you watch it at different times of the year going around the sun in this point of view. So Newton's connecting them. And the main goal of physics, you could say, is to make these deep connections between things that looked superficially, but very enticingly different. And then if you think about them long enough, or in the right way, you can show they're two parts of the same phenomenon. I wanted to also connect up with some of the items, and again, I can't see my title up here. That's unfortunate. This says Newton's assumption about space and time. So I'm going to gloss over all the nuance. There's so much to be said. We could have a whole course on, and in fact, we'll get into many of these subtleties, I assume, in Dr. Katavid's class. But this is just really cutting it down to the most bare basics, the assumptions Newton is making about space and time that I was kind of saying. In this course, we're going to assume that most of you are going to take for granted, and I'm happy to discuss why you may or may not do that, but it seems like my impression is most people don't consider these to be controversial, and they're going to come into question directly in this course. Einstein is going to call them into question. So someone said yesterday, space is like a kind of container in which things take place. You might call them events. Events is something, maybe two spheres colliding off of each other and bouncing. That would be an event. Usually we're going to make a very specific definition of an event. And an event is something that's kind of localized in space and time. So if a firecracker goes off right here, I didn't Do a good job snapping. My fingers are not with it today. That's an event. Another event is a different firecracker goes off here at a later time. Still can't snap this morning. There we go. So an event is something that's localized in space and time. More generally, you might just say an event is something that might have occurred. There's a location in space at a certain time where something might have occurred, even though maybe nothing occurred there. There was nothing nearby. We would still call that an event. So a space is a kind of container in which events might take place or do take place. A lot of times we're going to be concerned with things like a rocket leaves a planet on a trip to a distant star. That would be one event. It arrives at the distant star. That would be another event that occurs at a different location in space at a different time. Okay, so we asked about space. What about time? Well, Newton is going to think of time as a kind of parameter, and for different values, numerical values of this parameter, different objects are going to be at different locations in space. When we say an object might be large, so we could more generally say parts of objects. So as you run this parameter up and down from its numerical values, different objects move to different positions in space. Of course, we can't really do that. We can't control the parameter, but time is such a parameter. Okay, so here's so those are kind of a characterization of space and time for Newton. Again, glossing over all nuance. The time interval, how much time elapses, that's what I mean by the time interval, between two events. So firecracker goes off over here, then a firecracker goes off over here at a later time, different position in space. And the time interval between those two events could be measured by me with a stopwatch, by any one of you with a stopwatch. It hardly goes without saying, but we're going to call it into question, so we are saying it here, that time interval doesn't depend on who measures the time interval. In other words, we're all going to agree how much time elapsed between those two events. And it doesn't matter if the two events are close together or even in principle in one galaxy and another galaxy. It might be really hard to communicate with each other, but in principle, we would say if you use the correct definition of time, then everyone's going to agree with the time interval that elapsed between those two events. Okay, so there's lots of technical details about how one might measure that. An important special case of this is if you consider what events happen at the very same time. In other words, if we look at the events where the time interval between those events are 0 time. How did I say it here? If we identify a time at which a particular event occurs, everyone's going to agree about what events are simultaneous with that event at other points in space, even if they're at greatly distant locations in different galaxies, far, far away in the universe. Everyone should, in principle, agree. Otherwise, they're not using the correct definition of time. That's not what Newton means by time. So when we say something happened at a given time, that defines what's happening everywhere else in the universe at that particular time. There's a similar kind of relationship for space. The spatial distance between two events, in other words, those two firecracker events that occurred at different locations at different times, if we measure the distance between the locations in space where those two events occur, everyone should agree. There's not going to be a difference. There's nothing controversial about that, but we're going to call these into question in the coming chapters. In particular, the spatial distance between two simultaneous events. For example, we've got, a large, Star Wars kind of spaceship floating through space. At a certain instant in time, the location of the front of the ship, that would be an event. And at that same time, the location of the back of the ship. The distance between those two would give us the length of the ship at that particular time. So everyone's going to agree on lengths of objects, and therefore all the dimensions of objects and the volume of objects and things like that. All of these things on this slide are going to be called into question, and we'll see why in chapter 2 or 3. Okay, so that was just to make contact with what we talked about last time, and now let's go into chapter 1 and start with just a question that I want to ask you. We're imagining you're in a sleeper car of a old-fashioned train, but this is a very high-tech train. We're going to imagine this is like a magnetic levitation train, so you can't feel any of that vibration from the track as you're going down. It's completely smooth. You're on a long train trip, you awaken in the middle of the night, you look out the window and you see there's a train on a parallel track. And that train, when you look out the window, is going to your left from your point of view on a parallel track. And the question I want to ask you guys is, in which direction is your train moving? To the left? To the right? Neither? I gave, sometimes in my classes, and I didn't bother printing them this time, I will have like voting questions, just so I force you to take a point of view in answering a question. In which direction is your train moving? We can even, for those of you who are in class here, you can hold up fingers for your vote. Your train's moving left. Let's say A is 1 here, 1 finger. Right is 2. Your train's at rest, 3. Or D, it's impossible to tell. Let's just do a quick vote on that. See, I have these color-coded voting cards, and it's really easy for me to see the colors, but with your fingers, I have to really use some mental effort. I would say that, there are a few 3s and 4s, but basically the D's or 4s have it in here by pretty much a landslide. It's impossible to tell. Anybody want to put that into words, why it's impossible to tell? Again, we're assuming that you can't feel any vibration. This is the world's smoothest train. Or it could be something floating through outer space, right? You look out the window and you see some other spaceship going by you. And the question is, which direction is your spaceship moving? Anybody want to put it into words? Yeah. Well, yeah, I mean, we could say there's no way to experimentally tell between uniform motion and rest. In other words, so in this case, one possibility that our train is at rest. What does at rest mean here? Well, normally when we're on Earth, we mean at rest with respect to Earth. So I was sort of making that as a background assumption. I didn't want to make it too wordy here. But when I'm saying my train is moving left, I mean left from my point of view relative to Earth, like moving on Earth in that direction. At rest is at rest with respect to Earth. How about impossible to tell? Most of you are voting for, so that was a vote for 3, or at least the possibility of 3. We could say maybe everything fits into the container of 3. What about 4? Yes?
If you're going in a straight line at a constant speed, you won't be accelerating, so you won't feel all that you're moving. And so there's no way to differentiate your train moving versus the other train.
That's right. In other words, it may be that this train is at rest and my train's floating to the right. And when I look out the window, I'm going to see that train floating to the left. This isn't, this isn't something we practice as human beings very often, but it's one skill we're going to have to learn in this course is when you're looking at a set of events, they're always presented from someone's point of view. Here it's the point of view of the person who's looking out the window. But you might have to imagine several different points of view and how things would look from that point of view. So maybe I'm looking from the point of view of me sitting at rest with respect to the Earth, and those are floating to the left. Or maybe that train car that we're looking at is sitting at rest and we're moving to the right. Or there are lots of other possibilities you can think of. So yes, the answer is it's really impossible to tell, although there's some nuance here. In a sense, all of these are possible answers, but there's no way to say in particular which one is exactly true. Okay, so what I'm going to do, at least for the first half of today, with your help, and I'm going to try to state what was in chapter 1 of Merman's book, The Principle of Relativity, the idea of that principle in a lot of different words, and we're going to state it in greater and greater generality as we go on. Okay, and we're also going to practice quite a bit in moving between different points of view. So one statement of it is that one cannot tell by any experiment or introspection. I just put introspection in there because we're lots of philosophers in here too. Maybe you think by deeply looking inside yourself, you could feel whether you're moving or not. The statement, I mean, this is a definite statement and it's subject to experimental verification. One cannot tell by any experiment or introspection whether one is at rest or moving uniformly. Galileo thought of this in the following way, since he wasn't thinking of spaceships, that if someone were in a ship moving uniformly across the ocean, so they're in a big breeze and they're moving, getting blown at quite a clip across the ocean, if they took an object and threw it up, it would come right back down from their point of view vertically. Whereas if someone else were watching it, they would see that object go up and come back down in an arc, right? But from their point of view, from the point of view of the person on the ship, as long as the ship's not being tossed up and down, it's moving, we're assuming it's moving perfectly uniformly. There's no experiment that you could do if you were the person in that ship that could tell whether you're at rest or moving uniformly. So, for example, probably the more compelling point of view is from outer space, because there's no vibration, there's no wind in your face when you're in deep space. So here's an astronaut. I don't know where his home ship is, but he or she is floating in deep space, far from anything. And this astronaut thinks, well, I'm at rest. I mean, I just feel like I'm sitting here. There's nothing really to see, but I'm definitely at rest. And along comes another astronaut floating by. And this astronaut over here thinks this one's doing the moving. But of course, the astronaut over here is feeling just like they are at rest and the other one's doing the moving. So the principle of relativity is saying, first of all, there's no way to distinguish between these. And second of all, this statement is just relative. The statement of being at rest or being moving is one that is relative to a particular frame of reference. Okay, so that's one statement of the principle of relativity. Okay, in the train example, of course, that means you can't tell whether you're moving uniformly and the other train's at rest, or the other train is moving uniformly and you're at rest, or something in between. We'll flesh that out in a second. So we can measure our motion relative to other objects, but there's no fundamental sense in which the following statements are true. I am moving and the other train is at rest, or the other train is moving and I'm at rest, or both our trains are moving. There's lots of true statements you can make, and each one is true from a particular point of view, but none of them is fundamentally true, universally true. That's what I mean by fundamentally. Okay, let's try to just, before we do a little bit more practice, and I ask you to think about moving between different points of view, let's try to restate the principle of relativity in different words, because you'll see it stated different ways. And I think Merman does a little bit of this in chapter 1. So just to flesh out by any experiment what that means. If two identical experiments are performed under identical conditions, except one is done in a laboratory at rest and the other is done in a uniformly moving laboratory. In other words, when we say the laboratory, we mean all parts of the experiment are moving together. You can't interact with something that's not moving along with you, because then the whole experiment wouldn't be moving. So here the whole experiment is supposed to be moving together uniformly. The two experiments will have the same outcome. So that's just saying no matter what you do, you can't tell the difference between movement and being at rest. Okay? Different way of saying it. Since the laws of nature are supposed to be kind of a generalization of all possible experiments that you could do, we could restate this in terms of the laws of nature. The laws of nature are the same in a laboratory at rest as they are in any uniformly moving laboratory. Okay, that means the laws of nature are kind of a summary of all our experiments that we might perform. And then finally, you might say, well, if there's no difference between being at rest and any uniformly moving laboratory, most people define sitting at a state of rest, even though it sounds a little bit degenerate, to be moving uniformly. So I could say, if I'm moving at 1 meter per second in this direction, that's uniform movement. If I'm standing here still, that's uniform movement too. Why not? Because it's equivalent to all the others. So we could state it even more succinctly. The laws of nature are the same in any uniformly moving laboratory. Okay? That doesn't mean no matter what you do, you're not going to be able to tell whether you're moving relative to something else. I can tell whether I'm moving relative to the sun, but I can't tell whether Earth and sun are moving along at a great clip relative to everything else, or they're fundamentally at rest. That's what this is saying. Okay? You can tell your motion relative to other objects, but you can't tell motion full stop. Okay, let's practice with some of these, just to practice switching frames of reference here. Same setup as before. Now we're going to imagine a particular number that we imagine that the train, you somehow know that these cars are 16 meters long. Maybe I looked that up on the web. That's a typical freight car length. And they happen to be moving one freight car every second, so 16 meters per second. Somehow I know that. I can see that they're moving out the window, okay? You guys help me think, is it possible your train is at rest? And if so, in this case, how is the freight train moving relative to the ground? If we assume your train is at rest. Someone want to volunteer? I'm going to ask a lot of these, so they're going to get trickier as time goes on, so you might want to volunteer now. If we assume our freight train is at rest relative to the ground, so we're just sitting on the ground, how is the freight train moving relative to the ground? Yes? Yeah, it's moving at 16 meters per second relative to the ground. Of course, left from our point of view. Somebody else would say right if they were looking for that. But the point is, relative to the ground, they're moving at 16 meters per second. Okay, so that's one possibility. Let's suppose we know somehow that maybe we'll have a speedometer in our car, and we know our train is moving to the right at 16 meters per second. In that case, how is the freight train going to be moving relative to the ground? Somebody else help me. Just go ahead and shout it out. It would be at rest, 0 meters per second. Correct. So that's another possibility. Suppose, here's one that maybe is a step more difficult. Is it possible that the train that we're on is moving left? It's moving in that direction, left in the figure, at 16 meters per second. If that were the case, if it's possible, how would the freight train have to be moving relative to the ground? Yeah. At what speed? So, yes. So if our train is moving to the left at 16 meters per second, and we're moving relative to the ground at 16 meters per second to the left in the figure, and this train we're moving to the right at 16 meters per second. Would we see it when we look out the window? Would we see this? In other words, this assumption is we're still supposed to be seeing the same thing in all of these cases. We wouldn't. If we were moving in this direction and that train were moving in that direction, we would see it moving to the right. So I think that one can't be the case. Jack? That's right. I mean, we're using our usual kind of Newtonian assumptions here, and they're very, very close to correct. We'll see that we have to adjust these a little bit later on in the course. But for right now, just to practice moving between these points of view. If I know in 1 second my train moves 16 meters to the right, and in that same time, while I'm looking out the window, the train I'm looking at moves an additional 16 meters to the right, then relative to the ground, that train must have moved 32 meters to the right in that 1 second. Okay, we're having to think a little bit more in this one, right? Let's think a little bit more deeply. Any comments on that one? That one's not so easy as the first one or two, which were easier to imagine. Okay, so 32 meters per second. Ooh, okay, now they don't kind of match up anymore. Is it possible that the train that we're on is moving to the left at 10 meters per second, and yet I still look out the window and see the adjacent train moving at 16 meters per second? In that case, the freight train we're looking at, how fast would it have to be moving relative to the ground? Read. Yeah, 26. We're just adding them together in this particular case, right? Because our train moves 10, in 1 second, our train moves 10 meters in that direction. And the train adjacent to us moves 16 meters ahead of us. So if we add those together, it's moved 26 meters relative to the ground in 1 second. And that's one way to characterize what 26 meters per second is, okay? Just to belabor it, what if we're moving right? Our train is moving to the right at 4 meters per second. We look out the window and we see a train moving left at 16 meters per second. Yeah. That's right, because if it were at rest and we looked out the window at it, we would see it moving to the left at 4 meters per second. It's got to move in that time period an additional 12 meters to have moved 16 meters to the left every second. So 12 meters per second to the left. I think that's the last one on here. I know I'm belaboring the point. But this is something we don't do much in everyday life, is imagine how even we're used to saying, here I am, I'm either at rest here on the earth or I'm moving relative to earth. We've got this nice frame of reference which everything is measured relative to. We're going to be thinking a lot in this course about being in deep space where you have no reference points. You don't know which way is up or down, left or right, or anything like that. All you can see is how something is moving relative to you. And we're going to have to be able to flip between different points of view. Okay, here's a different statement of the principle of relativity. There's no one true description of the state of motion of objects. In other words, I can't say, fundamentally, this thing that's zipping through the room is moving at 4 meters per second. That's dependent on your point of view, right? That means, okay, I measured it at 4 meters per second because I was sitting in this room. But someone who's zipping in the other direction is going to measure a different speed, right? So assessments of how fast something is moving is not a fundamental description. There's no one true description. So here's just some pictures associated with this. Suppose one person observes that B is at rest and A is zipping to the right at 6 meters per second. That's one point of view. But, you know, we could take, that's the point of view of someone sitting at rest with B. What if you were sitting at rest with A or moving along with A? That means the same thing. If you're moving along with A, you would see B moving to the left at 6 meters per second. Right? Similar to the train examples. If instead, you know, from this first point of view, if I said, well, I'm going to move in the same direction as A, but I'm only going to move at 3 meters per second to the right. Well, then A is going to gain an additional 3 meters every second on me, and plus B is going to be moving to left at 3 meters per second. So this is another completely true description of events. And if I move to the left at 3 meters per second in this original point of view, relative to that, and observe it, I would see A moving to the right at 9 and B moving at 3. So we've got to get used to the fact that there's no one true velocity. We're used to measuring everything relative to Earth and not thinking about it here. Well, we're going to be imagining a lot of things in deep space, and there are lots of different true descriptions. There's no sense in which B is at rest and A is moving. That depends on who's looking at it, okay? Okay, so some further descriptions of these. Each description is equally valid. None of them is fundamentally true compared to the other ones. We can't experimentally distinguish which is actually the case. I'm not really sure what actually means, but we're saying that actually doesn't carry much weight here. There is no actual, they're all just relative to different points of view. There's no absolute sense to a description that means velocity or, you know, speed and direction of an object's motion. Objects move relative to each other, but the important point is they don't move relative to space itself. There's no sense, if you could say, hey, space is just sitting there and I'm moving relative to space, that you would have a claim that that object is moving and not at rest, if there were a sense of moving with respect to space. And that feels a little bit ungrounding because there's no absolute sense to who's moving and who's not. But when you're in deep space, if you put yourself out there with no points of reference, there's no way to tell whether you're moving at a very fast clip or just sitting at rest, because the feeling is exactly the same inside your body as long as you're moving uniformly. And I should say, I glossed over this, uniformly here means moving at a constant speed in a constant direction. We'll gloss over the fact of saying relative to what, and how do you determine that? That's a tough question to answer, but for the most part, we know it when we feel it. Here's another example. You know, we're actually moving really fast in some sense now. We're moving relative to the Earth's axis of spin at 900 kilometers per hour. That's pretty big speed relative to normal speeds on Earth, 900 kilometers per hour. Earth is moving relative to the sun at 100,000 kilometers per hour. The solar system is moving at 800,000 kilometers per hour relative to the galactic center, and yet we notice none of this motion. I feel perfectly still as I stand here right now, and that is sort of testament, or at least one indication, that there's no sense to us being fundamentally at motion or fundamentally at rest. Jack? That's right. So we are at rest in a sense. So if you know from being on carnival rides and things like that, or playground merry-go-rounds, that if you spin at a very fast rotation rate in a circle, you will actually feel the same. I mean, you can close your eyes and not see anything. Oh, I know I'm moving, right? I feel definite sensations in my body that I'm moving in a circle. In this case, even it's true, as we're here at a certain latitude on Earth, we're going in a circle. And if we were going in a circle fast enough, we would actually feel the sensation and notice effects associated with going in a circle. It's just that it's taking so long, 24 hours, to go around that circle, that it's so close to being moving uniformly in a straight line that we don't feel any effects. But technically we are. And you could do experiments actually to determine that you're not exactly doing it, but we certainly don't notice it with our bodies. So in this case, the idea is, hey, it's very close to moving in a straight line at any moment because the rate at which we're turning around in those circles is so small. But technically you could do experiments to show that you actually are not moving uniformly, but it's very close to uniform motion. So the principle of relativity, again, says we can observe our motion relative to other objects. Nobody disputes that. But objects in no way behave differently as long as they all move together uniformly. So if you take everything in your experiment and imagine it moving along all together uniformly, nothing would change in the experiments. I know I'm saying this many, many different ways. So we're going to do a worksheet now. Oh my gosh, I forgot this to the at-home people. That's one of the things I've got to remember. So what I'm going to do is bring it up after we start working on it. We're going to do one together in class now. After we start working on it, I apologize to you Zoom folks. What I'm going to do is bring up my copy on the camera, or sorry, on sharing my screen, and let you look at them while we're doing them. And normally I would consider, so I'm passing them out now. So just be patient, Zoom folks, while I'm handing these out to the class. Normally I would have you work in groups. It's a little bit difficult to work in groups. Some of you might want to talk in a good socially distanced way with someone adjacent to you if you want to discuss it. But just to get the idea, because these problems seem a little bit off-putting maybe the first time you read them. Okay, so let me show a particular graphic from this first one here, and I'm going to read it. once we get to problems 2 and 3 where you're supposed to be doing them yourselves, we're actually, I will put my version up on the screen and share the screen as we are now so that you guys at home can see it. The text here in problem 1 says, suppose we have two identical, perfectly elastic balls. Identical elastic balls have the property that if you shoot them directly at each other with the same speed, then after the collision, each bounces back in the same direction it came with the same speed it had before the collision. So these are like idealized, perfectly bouncy balls. So I'm imagining, just so that we can tell them apart here in this figure, one of them is white and one of them is black. And they're both moving at each other at equal and opposite speeds. You know, for most normal balls, they might bounce off of each other and lose a little bit of their speed in the final state, right? They might come in at a great clip and then bounce off at a lower speed. But in these idealized case, we're going to imagine that these perfectly bouncy balls, if they're coming at each other at 3 meters per second, they leave away from each other at 3 meters per second. We call those perfectly elastic balls. So that's what the first paragraph is saying. What happens, we want to ask now, what happens, so here's the same balls, perfectly elastic, equal mass balls, so they're identical in every way. They're still perfectly elastic. But now suppose I sit one at rest, the black one's at rest, and I fire the white one at it at 10 meters per second from the left. What would the final state look like? Well, at first it seems like I don't have a lot to go on there. Right? I don't have a lot to go on there. Can anybody see a way that I might transform this first state in the one at the bottom of the slide right now, the unknown state, how I could make this 10 meters per second and 0 meters per second state look like this one up here by just changing my point of view? This, you know, these are drawn from somebody's point of view, but from somebody else's point of view, things might look different, and I might be able to make this look like this. Yeah.
One going 10 meters a second, and the other direction you're traveling 10 meters per second in the way that the filled-in moments. The non-filled-in moments would be 10 meters per second to the right.
Okay, I think I see the idea you're doing, but I don't know that that's going to transform it into this case. In other words, let's suppose that you're standing here on a train station and you see this situation, the lower situation right there. And I want to ask, how could I jump on a train and have someone see a situation that looks like the one above? Because we know what happens in the final state if we can make them look like the one above. In other words, is there any point of view that we could take? How would the train have to be moving so that when I hop on the train, if this is what's being seen in the station down here, when I hop on the train, I see something that looks like this. I don't really care what those speeds are, but they've got to be equal and opposite, going exactly the same speeds in opposite directions. Can anybody see how I would have to move relative to the station to make that be true? Jack? That way, yeah, to the right in the figure, right? If we look at it from a point of view of a train moving to the right at 5 meters per second, the black ball that was previously at rest would be moving to the left at 5 meters per second, right? And if we're moving at 5 meters per second, in 1 second we move 5 meters in this direction. This ball moves 10 meters relative to the platforms, which means relative to us, it'll only move 5 meters further ahead of us. Again, we're practicing with this because this is not the kind of thinking we do in everyday life, and we're gonna be making arguments where we take different points of view, and we're not always doing that in everyday life because we're so stuck to the earth. Okay, so we're gonna imagine a train moving by at 5 meters per second, and from that point of view, from the train's point of view, one ball would be moving to the left at 5 meters per second, and one ball would be moving to the right at 5 meters per second. And that means I can immediately conclude what would happen in the final state from the point of view of the train. The train sees this happening, the left one here. I should be pointing with my digital laser pointer so the folks at home can see. From the train point of view, this is what happens in the initial state, and we said, hey, they're perfectly elastic balls. By definition, if you like, this is what's going to happen in the final state. So I know what the train is seeing in the final state. What should the station then be seeing in the final state? Can anybody transform back? If this is what the train is seeing, and it's moving at 5 meters per second relative to the station, what is the black ball going to be doing relative to the station? Yes? Yeah, because relative to the station, the train is moving to the right 5 meters every second. And they're also seeing the ball moving 5 additional meters ahead of the train every second. So that means relative to the station, it's going to move 10 additional meters to the right. Okay? And if the train is moving to the right at 10 meters per second, and on the train, they see the white ball moving to the left at 5 meters per second. Can anybody see? And I know this makes your mind twist a little bit. It's not immediately obvious. You really have to kind of contort your brain to see this. But that's why we're practicing it now. You're going to see these arguments, kinds of arguments coming up where you change points of view. Can anybody see what the white ball's motion would be in the station in the final state? It would be at rest, right? Because if a white ball were at rest and you're moving at 5 meters per second to the right, you're going to see it as moving at 5 meters per second to the left. Okay, so that tells us, wow, we learned a lot just by knowing what happens in one point of view, that elastic balls behave like this. If we see some other situation, we can automatically conclude, well, maybe not automatically, it takes some brain power. You've really got to think hard. But we can conclude what happens in another point of view. So there's not much work to be shown here, but you really do have to put yourself on that train, which is not necessarily easy. So what I'm going to do now is I'm going to stop sharing for just a second and pull up my version of this. What I'd like you to do is work on problems 2 and 3. I'm going to open mine up and then share it with the Zoom folks, and I apologize again. It was on my list this morning to email this before class, and then I got distracted by my new camera and meeting ITS over here. So let's see. This looks like it. Okay. Let's share the screen again. So here, maybe I don't know if I can fit this all on here at once, but for those of you who are zooming in, we're working on problem 2, at least initially. I can't quite fit it all on here, and I don't want to make it too small. Problem 3 is shown down below. So problems 2 and 3 are what we're working on. Problem 2 concerns balls that are the opposite of elastic. It's like they're covered in Velcro. So every time they strike each other, they just stick together. And so the one easy point of view is if I have equal mass, 2 equal mass balls, and they're covered in opposite kinds of Velcro, if they come together with equal and opposite velocities, by symmetry, they just have to stick and be at rest. They're coming with equal and opposite velocities, and by definition, they stick. That's called completely inelastic collisions. Then what would happen in the same case that we asked about before, where one of them is moving to the right at 10 meters per second and strikes the other one at rest, and they stick together? What would you see in that point of view? And for you Zoom folks, if you have a question, just jump on in, unmute yourself and ask, and I'll run over and try to see what's happening and help you out. Same thing for those of you in the room. If you're having trouble getting started, feel free to raise your hand. This is not an exam, so if you're not understanding the point of it or don't know what the first step to take, please raise your hand. Normally this is something that where I rely on you talking to your partner that you're working with, but I know you're all trying to stay nicely far apart. Feel free to talk, you know, with whoever's closest to you if you're having trouble getting started, or if you just want to see what they got once you finish. I think someone's missing. Before I call roll, does anybody know who's not in class? I see Jacob Walterman. I see Royce. I see Chen Zeng and Camacho on there. Does anybody, I know you don't all know each other's names yet. And it's hard for me to learn people's faces with their masks on, but I will eventually. I just get used to seeing people with their masks on and know what they look like. Nobody knows who's here. I'm gonna, because I forgot my roll sheet, I'm just gonna quickly call roll here. Why can I not move this? Okay, there we go. Come on. Okay, Camacho I saw. Everett Hauser. Okay. Hannah Jackson. Oh, it's Richard. Muchiri. Muchiri's not on here. And I don't
I'm
know
here.
if he appeared on. Oh, no.
I'm in class.
He said he was having trouble connecting yesterday, and
Yeah, he's here.
maybe he's dropped out.
He's
We'll
present.
look for him. It's
He's
Muchiri
here.
that's not on.
No, he
No.
is here.
Hey, Dr. Kelly. Oops. Oh, yeah.
Mushiri, I see you. I will let him know unless he notices. Okay?
Okay. Okay, yeah. Okay, sure.
So notice I'm helping you out a little bit here by saying the point of view that you should be taking in problem 2. It will pay off if you view things from the point of view of a train going by the description that's given at 5 meters per second and try to figure out what it would see. It transforms it into the case that you know. But you've still got to do the thinking to know, then how do I transform back to figure out what would be seen in the station? The answer in 2 is 5 meters per second. I don't know if you guys, anybody agree with that? Should the two are stuck together and moving to the right at 5 meters per second. And you know, the picture almost shows all of it right here. Oh no, you don't see them. No, you do. I'm sorry, I'm looking at the wrong one here. If the train moves to the right at 5 meters per second, then something that was moving to the right at 10 would be seen as moving to the right at 5, and something that were stationary would be seen as moving left at 5. And so that transforms this situation into the case of on the train, you would see something that looks like this, where they were going equal and opposite at 5, and they would be at rest afterwards from the train's point of view. If they're at rest afterwards in the frame of the train, that means they're moving along with the train. So they're moving to the right at 5 meters per second. The third situation concerns two elastic balls, but in this case, they have very different masses. One's like a ping pong ball and the other one's like a bowling ball. So it may as well be a brick wall as far as the ping pong ball is concerned. And the idea is if they're perfectly elastic. So the idea is, in this case, if an elastic ball bounces off another elastic ball and that other one's really massive, it basically just reverses its direction. No energy or speed is lost in the collision if they're perfectly elastic. So that's something we know. And the question is then, well, what if I reverse the roles? What if I put the ping pong ball at rest and I throw the bowling ball at it at 10 meters per second? What is the final situation going to look like there? And again, I've got to figure out how to ride on a train, and I really essentially told you how to do it here. From the train's point of view, we're going to transform the station point of view into the case that we know. I'll give you another minute to think about it. We'll discuss the solution to this one. So the idea is we know if a ping pong ball hits a bowling ball, it bounces off in the opposite direction. And though the bowling ball might move a tiny bit, it's essentially still at rest afterwards for all practical purposes. It's going to move a little tiny bit in the direction it gets hit, but if the masses are really unequal, it's hardly going to move at all. And from knowing that, how can we transform this point of view into the other point of view? Okay, so just, I'm not sure how people are doing with this, but let's come together now. So let me stop sharing the screen. And hopefully, Chen, again, can you give me a thumbs up if you're seeing this screen in the right orientation? Is the writing backwards? It looks good? Okay. Because from my point of view, it's reversed. And that's probably for the benefit of me so that when I look at this, it looks like I'm looking into a mirror, but you don't want to see a mirror because all the words would be reversed. I see I'm a little bit off center here. So the idea is in the station, so what we know is that if the bowling ball is sitting at rest, that's not pictured on here. If the bowling ball is sitting at rest and the ping pong ball comes in at 10 meters per second or 5 meters per second, it just leaves with the same speed in the other direction. It's like it bounced off a brick wall and it didn't lose any energy. That's the kind of balls that these are. They don't lose much energy in their collisions. Is there any, so now we're asking a different question. If the ping pong ball is at rest and the bowling ball comes along at 10 meters per second going to the left, what's the final state look like afterwards over here? And in other words, the way we're going to answer it is, how would we move relative to the station to turn this into a situation where the bowling ball appeared at rest and the ping pong ball was the only thing moving? Well, if I want the bowling ball to be at rest, I better move along with the bowling ball. So I better jump on a train that's moving at the same speed in the same direction relative to the station. That's moving at 10 meters per second to the left in this particular view of the figure. And from that point of view, what speed would the bowling ball have from the train's point of view? 0, right? So in this point of view, this would be at rest. And what about the ping pong ball? It's going to be moving 10 meters per second to the right. And that's exactly a case that I know something about. You have to believe that these are the kind of balls that behave the way described in the first paragraph, that this ping pong ball comes in, hits the bowling ball, it doesn't lose any energy, so it comes in at 10, it goes out at 10. The bowling ball is, for all practical purposes, at rest in the final state, okay? So from the train's point of view, I know what happens in this state. The bowling ball, well, I know technically it would be moving a tiny bit to the right, but if its mass is really huge, it's essentially still at rest after the collision, and the ping pong ball is moving to the left at 10. So that's what's happening from the train's point of view in the final state. And now I can conclude what's happening in the station's point of view by imagining, if you see this happening from this point of view, what must have been happening in the station. So what's the bowling ball doing after the collision in the station? Still going at 10. In other words, if the train looks at this and sees the bowling ball at rest, that means the bowling ball's moving along with the train, and the train's moving relative to the station at 10 meters per second. I know this makes you twist your brain around in a way that none of us are probably used to. But if it's at rest from the point of view of the train, that means it's moving along with the train. So relative to the station, it's moving to the left at 10 meters per second. Probably not surprising, because it ran into a puny ping pong ball, just blasted it out of the way, and it hardly changed its speed at all, right? That kind of makes sense. What's maybe not as obvious is what's going on with the ping pong ball. If the train is moving at 10 meters per second relative to the station, and the ping pong ball is moving 10 meters per second even in the same direction relative to the train, what's it doing relative to the station? It's moving at 20 to the left. Okay, that's not immediately obvious. So this comes in and slams into it. It ends up shooting it ahead at twice the speed at which the bowling ball was coming in at. Now, if you're getting a little bit nervous and thinking, oh boy, you know, these puzzles of thinking about, it is going to be important in some of the derivations to switch between points of view like this. This type of problem is not going to be extremely important for the kinds of things that come ahead. But the reason we're doing this is to practice thinking of things from several different points of view, because the claim we made is that no point of view is fundamentally true. All right. Any more questions before we finish up with the last few slides? Oops, I don't want to do that. Okay, let's share screen again. Go back to the slides here. Okay, I believe that one of the other things you read about, or at least I'm introducing it here, does Merman talk about the notion of an inertial reference frame in chapter 1? Okay, good. So here's a definition, my own words, an inertial reference frame, and I'm going to abbreviate that. I know it's obscured by that little thing at the top here. We'll use that word so often that it's kind of cumbersome to write down inertial reference frame or even say it. So I'm just going to call it IRF. I'm not a huge person who likes very short acronyms for things, but occasionally I will choose something that helps save a lot of effort. So IRF is inertial reference frame, is the perspective of an observer who moves uniformly, from which events can be viewed or measurements made. So, you know, if something's happening, like these collisions between some balls, you could observe it from lots of different points of view. Of particular importance to us will be inertial reference frame points of view. In other words, we're not going to include in inertial reference frames people who were accelerating or moving in circles really fast. Those won't be inertial reference frame. But if you're moving uniformly, constant speed, constant direction, then there's lots of different ways to view things, okay? Now, here's a fact. The perspective of so once you decide that your perspective is an inertial reference frame, the perspective of any other observer who moves uniformly with respect to you is another inertial reference frame. In other words, if I somehow know I'm moving uniformly, maybe I just feel it in my gut. I would know if I were accelerating, right? You feel yourself pressed against the seat. Or if you're going in a circle, you kind of feel thrown to the outside or things like that. So I'm out in outer space. I feel like I'm at rest. So it seems like I'm an inertial reference frame. I see another thing go by me at a constant velocity, constant speed, and constant direction. That's what constant velocity means. Then that's another inertial reference frame. And of course, there are an infinite number of inertial reference frames, an infinite number of points of view that we could view events from. And that's somewhat disconcerting, but so we'll take advantage of it quite a bit in this course. So the collection of all those uniformly moving observers is the totality of all inertial reference frames. Now, we're going to envision kind of an elaborate inertial reference frame because, you know, oftentimes we're going to want to measure things that happen very far away in the universe, maybe here and in a distant galaxy, and there's not enough time to travel there between the two events. So we can't just rely on one observer. So we're going to have a whole bunch of observers who are all moving together uniformly. So we're going to assume, along with each inertial reference frame, it has at its disposal a lattice of meter sticks. In other words, we're going to use these to measure x, y, z coordinates, points in three-dimensional space. By a lattice, I mean, you know, you just form something that's like a crystal kind of out of these, you know, build a big structure out of meter sticks going in all three directions. I'll show you a visualization in just a second. There's also a collection of synchronized clocks. We're going to have a clock at every local position in this lattice because if I want to measure something at a particular time, it's hard for me to communicate instantaneously from someone who's galaxies away from me that we need to measure something at the same time from our point of view. And so we better have a bunch of synchronized clocks in there that are going to be at the location of lots of different events. And we're going to imagine that there's someone who rides along with all of these things locally at every position in the lattice. Now, I know that sounds completely excessive, but it's to pin down exactly what we mean by a measurement of the location of something in space and the time at which it happened in space. We're going to imagine that no matter what interesting event happens anywhere in the universe, from my point of view, my IRF that I'm riding along with, I have another observer on my team who is right there at that event, who can measure exactly what its X, Y, Z coordinates were, exactly what time it happened at. I don't have to wait for, you know, signals that he sends back to me and then have to subtract the travel time or all those complications, okay? So using this, we won't have to worry about making or interpreting remote measurements of events, like looking through a telescope and saying, oh, the light took time to get to me, so when I see it happen, it wasn't actually happening at that time, it happened at an earlier time. We're going to have someone right there who doesn't have any delay in the information getting to them. So here's a famous picture from a book I was telling Jack about yesterday, Wheeler and Taylor, Space-Time Physics. It's sort of a calculus-based book for introductory relativity, but if you're interested in it, it's worthwhile looking at. So this is kind of a picture of what Wheeler and Taylor say you could envision an inertial reference frame being. It's like this structure made out of meter sticks. So this is a meter stick on the bottom here. This is a meter stick. This is a meter stick. This is a clock. Here's another clock. Here's another clock. So there are clocks everywhere in this lattice. There are meter sticks everywhere. The meter sticks presumably are, you know, at somewhere there's an origin, and there, you know, the x coordinate keeps going up and up and up and up and up on those meter sticks as you go farther to the right. And we're going to imagine that in principle, we could set this up so that they were everywhere in the universe. Of course, they'd be colliding with things everywhere, but at least this is going to, in our minds, be definite about what it means to say, oh, an event happened, a firecracker went off somewhere in the universe. Someone can record the XYZ coordinates and the time at which it happened, and they will be present right when it went off at that location. We don't have to wait for any delay of information to get to them. So that's the idea of an IRF, inertial reference frame. So the idea with lots of different inertial reference frames in this figure is that, you know, something interesting happens. Maybe these two spheres collide and careen off of each other. We could view those events from lots of different IRFs. And of course, we should really be imagining these IRFs all extend to the point where they would go here and they would be colliding with each other. It would be tons of practical problems, but we're not going to worry about those practical problems. We're just going to take it to be an in principle thing that someone in each of these inertial reference frame, this one's moving up and to the right, this one's moving somewhat to the left, this one's moving really fast up and to the left. All of them would have their local observers that were present in this region, and they could measure in their own coordinate system what the X, Y, Z coordinate systems coordinate of the event was, and what the time coordinate of the event was, what it said on their clock. Okay. Okay, so phrased in terms of inertial reference frames, the principle of relativity, and I can't remember, I think Merman uses a different shorthand for this. It's maybe principle 1 or something, or does he call it PR? He calls it PR. Okay, so I got this from Merman. Just as shorthand, because when we use the principle of relativity, it's going to be something we bring in as an assumption all the time in derivation. So Einstein's going to assume that the principle of relativity applies. So PR is short for phrased in terms of IRFs. Again, I'm promising I'm not going to give tons of acronyms in this course. Although events may look different in different IRFs, they obey the same laws of physics in every IRF. Each IRF is just as good as any other. So here's a statement we might make in everyday language. I believe this is straight from Merman's book. Mr. Wilkins is at rest. Well, that's a statement that makes sense in everyday language, and we know the person meant relative to Earth. But it certainly isn't universally true. If someone's zooming by at 86,000 meters per second by that person doesn't look to be at rest, Mr. Wilkins, whatever he's doing. So it's not a universally true statement. Here's a universally true restatement of it that is perhaps too cumbersome. Mr. Wilkins is either at rest or moving uniformly, depending on which of all the equally good laboratories you choose to measure his speed from. Now, we're not going to want to say things like that in this course either. So rather than saying that, we're going to use IRF as a shorthand. Another way of saying that really big paragraph is that Mr. Wilkins is in an IRF, in an inertial reference frame. In other words, it's just as good as being at rest. Someone will say he's at rest. Mr. Wilkins will probably say he's at rest. But other people would say, well, you know, just as good as being at rest, you're in an inertial reference frame, some inertial reference frame. Okay, the last prickly issue is, well, what is uniform motion? We sort of glossed over this earlier, and Merman gives a pragmatic answer. A uniform motion is just simply motion with constant speed in a constant direction. If a point on the object ever changes either its speed or its direction, its motion we're going to call non-uniform. Now that glosses over something, especially if you're philosophically minded, that is a difficult problem and is never really resolved by Merman. Okay, and that is, well, how do you know that the motion is uniform and with constant speed, constant direction? How do you know? Maybe I'm looking at something and I feel like I'm at rest, but I'm actually fundamentally, in some sense, not moving uniformly. And when I look at something, it looks at rest with respect to me, or maybe it looks like it's moving with constant velocity, but really we're both not moving uniformly together, and so I wouldn't know. We're not really going to give a good answer to how to think about that, okay? What's Newton's answer to this? Newton's answer for how to determine whether an inertial reference frame is, whether something is an inertial reference frame, is one in which Newton's first law is true. So we got to state Newton's first law. We'll talk about his other laws a little bit later on in the course. Newton's first law, many have heard this kind of thing before, but this is my own restatement of it. When viewed from an inertial reference frame, any object with no forces acting on it is measured to move with constant speed and constant direction. So that means I have to not only look for things that are moving with constant speed and constant direction, but be assured that there are no forces acting on it. And sometimes I can sort of at least qualitatively be assured of that by being in deep space and say, oh, an asteroid floats by. Well, let's see. It looks like it's moving at constant speed and constant direction, but are there any forces on it? And I look around, there's no great sources of gravitation, right? No big masses nearby it that would cause it to be attracted to those objects. It's not near a star or any other big mass. There's nothing that's electrically charged that would cause the charge to move it in a non-uniform way, and so on. Okay, so for example, this here again is a fanciful example of someone sitting in outer space watching this rocket go by at a uniform speed, and they reason to themselves, I don't see any forces that should be acting on the ship. In other words, there's no great gravitational sources nearby, no big stars or planets that it would be curved by. And I'm observing that it's moving with constant speed and direction, and therefore that's some amount of evidence that because I see an object with no forces on it, moving with constant speed and direction, that I'm observing from an inertial reference frame. It's sort of a backwards way of thinking about what it means, okay? Maybe I'll stop there and we'll finish up with this the next time. There's a last couple of questions there. Anybody want to ask any questions before we break for the day? I'm trying to keep our meetings to 1 hour and 15 minutes. And with the worksheet, we went a little bit over today. Okay, so we'll come back and reconnect with this idea of how do I know I'm observing something from an inertial reference frame next time. And I guess for those of you who are here in class, I will see you in the tent in not too long. And for the rest of you, if you're at home, I'll see you at our next meeting. And by the way, I should say again that if you want to stay for office hours, those happen every day right after the end of class. So that means right now, if you have any questions, you're welcome to hang out. Same thing for those of you who are on Zoom. Just hang out and shout out your question to get my attention, and we can get you helped. Otherwise, I'll see you, some of you, in the tent in not too long.
Yeah, I missed it.
All right. See you later, anyway.
Yeah, I forgot.